Jai Hind, welcome to class of Satellite and Radar Systems. This is REC 083. We are studying Unit 1 and this is Part 3. So today we'll be covering look angles, orbit determination, launches and launch vehicles, and finally orbital elements. There will be including some of the basic definitions of satellite communication. So first of all, what are look angles? As the name suggests, look angles. So these are the angles at which your earth station must be pointed, so that communication between the satellite and the receiving earth station must be good, right? So the coordinates to which an earth station must be pointed to communicate with the satellite are called as look angles. So we have two look angles, azimuthal angle and elevation angle. This is also called as azimuth angle, we can call it azimuthal angle, and the second one is elevation angle. Combiningly, these two angles are called as look angles. Generally, value of these angles, they do change for non-stationary, non-geostationary orbits, but as we know that geostationary or geosynchronous satellites are fixed on they are looking at a particular area on Earth, so there doesn't changes for geostationary satellites, whereas these values are changed for your other orbit satellites. So with this picture we can see how look angles can be shown. So if I consider this my satellite and the directions, this is the local vertical, which is 90 degree to the horizontal plane is called as local vertical. So when we take projections of satellite, projection of path on local horizontal will give me azimuthal angle, and this line, with the help of this path of satellite, I can get to know about my elevation angle. This will be more clear when we see its definition. So what do we mean by azimuth angle? This is the angle between local horizontal plane and the plane passing through the earth station. So we have to take angle between local horizontal, from where we are taking this angles on the earth surface. We have to consider that local horizontal plane and the plane passing through the earth station, the satellite and the center of earth. That angle is your azimuth angle. This can be depicted from the picture here. If this is my satellite, this this direction I consider east to west and this north to south. If I divide my earth into two hemispheres, with the help of these axes, that is joining north and south, and axis joining west and east, then when I see the projection of satellite on local horizontal plane, and when I join it from the center, the angle that it makes with the vertical line, that is my azimuthal angle, this angle. So this angle is very important. Later on we will be using it for numerical as well. So a formula for calculation of azimuth angle can be expressed as alpha, and alpha can be calculated as 180 degree plus tan inverse of tan G by tan L, where L is the latitude of earth station antenna and G is the difference between position of satellite orbit and earth station antenna. So tan of the difference between the ratio tan inverse of this ratio, where this ratio can be known from here. So azimuth angle can be calculated mathematically using this formula. This is important, right? This picture we have already seen. What about elevation angle? Elevation angle, it is the angle between vertical plane and line pointing to satellite, right? So let's see how. So vertical plane is what? It is perpendicular to the horizontal plane. Horizontal plane is the local plane where we see the projection of satellite. If we draw a perpendicular line to that horizontal plane, that will be the vertical plane. Now the angle between that vertical plane and line pointing to satellite, this can be shown from this picture, right? So this is my earth station, this is the satellite. So from the definition we can see that the angle between vertical plane and line pointing to satellite, vertical plane and line pointing to satellite. If I consider this as my vertical plane, if this line I have drawn by considering it to be perpendicular to the local horizontal plane, right? So vertical plane can be drawn 90 degree to the local horizontal, and the angle between projection of satellite and that vertical plane is gives me elevation angle, right? So both these angles are depicted in this picture here. We can see the difference, right? And how do we calculate? Elevation angle is represented by beta, azimuth angle we are representing by alpha, and elevation angle we are representing by beta. So beta is given as tan inverse of cos g cos L minus 0.15 by under root of 1 minus cos square g cos square L. Value of g, what are your g and L? G is the difference between position of satellite orbit and earth station antenna, and L is the latitude of earth station antenna. These values remain same, right? L is the same entity, G is the same entity for azimuth angle and elevation angle, right? So using these two formula we can calculate look angles, that is azimuth angle and elevation angle, right? Next thing we will be studying about orbital perturbations. So what are perturbations? Any deformity or any deviation from the actual path. So when we are talking about orbital perturbations, then when my satellite deviates from the actual or ideal orbit, that will be called as perturbation. So the question is why these perturbations arises. Like we do launch satellite in a particular orbit and mechanize the process in a way that satellite always revolves around Earth in that fixed orbit, following that fixed path, fixed direction, fixed movement, that fixed elliptical path with that fixed height from Earth's surface. Then how later on how do these changes and what can we do to help them? Right. So first we will be studying about what are the reasons behind these perturbations. So these perturbations could be due to gravitational and non-gravitational forces. We place a satellite, fixing its the forces are balanced in a way that centripetal and centrifugal forces, they balance out each other and the satellite remains fixed in its orbit. But with time, gradually, if it is somehow closer to the Earth's surface, there will be gravitational pull. It will be somehow attracting the satellite a little and there will be some deviation from its path. There are other forces also in the solar system that may cause that satellite to deviate from its actual ideal path. So the reasons are enlisted here. The irregular gravitational force around the Earth due to non-uniform mass distribution. We know inside Earth's surface, inside the Earth we have heavy metals. Somewhere these heavy metals are dense, somewhere inside the composition varies. So gravitational force also depends on the composition of Earth. So these gravitational forces are also irregular because of non-uniform mass distribution. And because of non-uniform mass distribution, we at times face magnetic field is also variable at different point. So because of the variation of gravitational force and magnetic field, we do face some perturbation, right? These forces act on satellite in a way that they are somehow deviated from their path. Now the question is, do they act in similar manner to low Earth orbit, medium Earth orbit and geostationary orbit? No. LEO satellites, that is low Earth orbit satellites, are closer to Earth's surface. So gravitational pull is more dominant in LEO. right? So low Earth orbit satellites are more affected by gravitational pull as compared to MEO or GEO, right? So this is due to friction caused by collision with atoms and ions which are closer to Earth's surface, right? The next thing is there are solar radiation pressures also, right? And solar radiation pressures, they affect they are more dominant and they are more visible on GEO satellite orbits, right? So at that high there are more amount of solar radiation pressures, so which use large solar arrays, right? Your geosatellites, they use large solar arrays, so even pressure. Geostationary satellites are somehow bigger in size. They are placed at a particular height that is approximately 36,000 kilometers from Earth's surface. So because of larger solar panels, solar radiation pressures are also larger on them, right? Now next reason is self-generated torques and pressures caused by RF radiation from the antenna. Even our satellite, they are equipped with antennas. At times there are torques and pressure generated within themselves. So a little bit force will make them deviate from its path. So these are the things, in spite of exact calculation and well monitored placing and well monitored mechanism of satellite movement, there are some reasons because of which satellites, they do deviate from their path with time. So there are remedies to this as well. We have various means by which these can be fixed, which we'll be covering in our upcoming lectures, right? So now if we talk about launching of satellites, so these are the topics that we are covering. Let's go to the content again. So we are talking about look angles that we have covered. Orbit determination is with the help of look angles, and now we'll study about launches and launch vehicles. Ever imagined how a satellite is launched into its fixed orbit? Making a satellite is a separate task. Then launching or placing a satellite in its orbit is a separate task. This is a whole lot of tasks. This is well planned. These plannings are done years before. Making a satellite, that we allot a particular time for designing a satellite. Then launching a satellite involves so many factors that should be considered. The weather conditions, there are finances associated with. Government bodies are doing the task, because no sole body can do such big tasks, because there are finances associated, there is space associated, a lot of planning, engineering is involved. So launching of satellite is one precise thing that will make the whole lot of process of designing a satellite worth, because designing and launching is very expensive process, and if not launched into fixed orbit, particular orbit that we have planned, then the purpose of placing a satellite will not be fulfilled, right? The essence of doing it will be lost. We do launch a satellite in a fixed orbit so that we can gain something out of it, right? So launching is very important in satellite communication, so it is studied as a separate topic. So launching of satellite involves several stages, right? So these stages, we can name it like first stage, second stage, third stage, and the fourth stage, right? So the first stage involves your rockets, right? So most of the fuel get consumed in taking the satellite away from gravitational pull, right? So most of the fuel get consumed in taking our satellite to few kilometers beyond Earth's surface, where the gravitational pull becomes negligible. So the first stage of launch vehicle contains rockets and fuel for lifting the satellite along with the launch vehicle from ground, right? So these are heavy tanks are associated with the rocket, and when the rocket goes, it usually takes parabolic path, right, because straight it cannot go up straight beyond Earth's surface. So when most of the fuel get consumed, it sheds its part. Most of the time it sheds its part. So based on whether these parts can be reused or not, we have divided or categorized our launch vehicles also, which we will be studying next. So about the first stage, so it contains rocket. If we talk about the second stage of launch vehicle contains small rockets, right. These are ignited after completion of first stage. Now the first stage are big rockets, big fuel tank to take it beyond the Earth's gravitational pull. Later, to provide it direction, we need small rockets. These are ignited after completion of first stages. All are manually controlled at Earth station. Big team of scientists are involved, and a lot of mechanism and softwares are involved in doing this, right. They have their own fuel tanks in order to send the satellite into space, right. Next, the third stage, that is upper stage of the launch vehicle, is connected to satellite fairing, right. This fairing is a metal shield which contains the satellite and protects the satellite. We just don't put satellite directly into space, that is protected, that is covered initially. So in the third stage, launch vehicle is connected to satellite fairing. So it is usually a metal shield, right, and it prevents the satellite from the friction which occurs when the rocket moves upward. In the fourth stage, the satellite gets separated from the upper stage of the launch vehicle. We have fuel tank, that is big rocket, we have small rockets, then we have metal shield. Then in the fourth stage, the satellite gets separated from the upper stage of the launch vehicle. Now when it has been reached to outer of Earth's atmosphere, then the satellite would go into transfer orbit. This orbit sends the satellite higher into space, and once the satellite reaches its desired position, the solar panel will open now and the satellite will expand and take its actual structure, right. Before that, solar panels are closed, all antennas are within a box like structure. All this open up when the satellite reaches its exact and actual orbit. So when the satellite reached to the desired height of the orbit, its subsystem like solar panels, communication, antenna, they get unfurled, right. Then the satellite takes its position into the orbit with other satellite. Now the satellite is ready to provide services to the public. So in order to make this happen, that is to start the services, a satellite needs to be placed into its orbit. Here in this picture we can see these are the solar panels. Initially these are closed. Once it reaches its orbit, these are opened, flared, right. So launching is a very critical, very important, time consuming, finance consuming, and one of the most important thing in satellite communication. So let's get to know a few things about various launch vehicles. Satellite launch vehicles launch the satellite into particular orbit based on the requirement. So these are categorized as expandable and reusable, right. Expandable launch vehicles, ELVs, and reusable launch vehicles, RLVs. Let's see. What are expandable launch vehicles? Expandable launch vehicles, they are destroyed after leaving the satellite in space. Once the rocket or once the launch vehicle leaves the satellite into space, they are just roaming around in space and act as debris. They are of no use, right. So they don't come back to Earth, we cannot reuse them. So they are just left out in space, and space is a big endless thing. So they just keep they are just there forever. So the ELV contain 3 stages. The first and second stages of ELV raise the satellite to about 50 miles and 100 miles, and the third stage is the stage where satellite is actually placed into orbit. So this is done in stages. First stage, it crosses the Earth's gravitational pull. Second stage, it reaches close to orbit. In third state it reaches the exact orbit. The task of ELV will be completed and its spare parts will be fallen to earth. In few cases it may fall to earth, in few cases where it has reached beyond earth's gravitational pull, it will be just roaming around in space when the satellite reaches to the transfer orbits. ELV somehow looks like this. This is a real picture. Now what are RLVs, reusable launch vehicles? RLVs can be used multiple times for launching satellites, right? When the parts are shed, they are collected back for second launching. Generally, this type of launch vehicles will return back to Earth after leaving the satellite in space. The functions of space shuttle are similar to functions of the first and stages of ELV. Stages are similar. Satellite along with the third stage of space shuttle are mounted in the cargo bay, right? It is ejected from the cargo bay when the space shuttle reaches to an elevation of 150 to 200 miles. Then the third stage of space shuttle gets fired and places the satellite into a transfer orbit, and after this the space shuttle will return back to Earth for reuse. When it falls to Earth's surface, they are in a position to be reused. So that is the difference. When ELV's parts expanded are not reused, for RLVs these parts are reused. This somehow shows a reusable launch vehicle. It is also known as space shuttle. So space shuttles are reused, right? So this was about launching process and launch vehicles. We'll study launching in detail when we study about geostationary, how a satellite is placed into geostationary orbit. There are stages. When does the kick motor starts, how rocket gets ignited, what are the fuel that we use for it. We'll study a whole lot of this in detail. Now there are few definitions that need to be studied before we go into depth of satellite communication. Semi-major axis, eccentricity, mean anomaly, argument of perigee, inclination, right ascension of ascending node. These are called as the orbital elements. These are 6 basic and important orbital elements. Their definition we must know. What is semi-major axis? We know that path of a satellite is elliptical around Earth, right? So an ellipse has 2 axes, the minor axis and the major axis. Half of the major axis is called as semi-major axis. We know ellipse has 2 foci. These are named as F1 and F2, foci 1 and foci 2. This is the center. So this half portion is called as semi-major axis. This is written as small a. The length of semi-major axis, small a, defines the size of satellite's orbit. It's half of the semi-major axis. It also is used for calculation of time period of revolution. If circular orbit is considered as special case, then the length of semi-major axis will be equal to radius of the circular orbit. This is the case of your geostationary satellites. In case of geostationary satellites, the path is not elliptical. This is one of the exceptions of Kepler's law, first law, right? Path of a geostationary satellite is always circular. In that case, the value of small a, semi-major axis, can be replaced with the radius of Earth. Eccentricity. Eccentricity is denoted by small e. Eccentricity fixes the shape of satellite's orbit. Like we know that value of eccentricity for circle is 0, and eccentricity will be maximum in case of an ellipse with infinite semi-major axis, right? The length of and how can be calculated? If I have an ellipse with semi-major axis represented by small a and semi-minor axis represented by small b, then eccentricity can be calculated by that mathematical formula, under root of a square minus b square by a. The value of eccentricity for a circular orbit is 0, we know, right? Because both a and b are equal. What is mean anomaly? Mean anomaly basically gives the average value of angular position of satellite with reference to the perigee. We know that perigee is the distance of satellite when it comes closest to Earth. and apogee is the distance of the satellite when it is farthest to Earth, right? So it is, for satellite, the point which is closest to Earth, we know that is perigee, and mean anomaly gives the average value of angular position of the satellite with reference to perigee. If the orbit is circular, then mean anomaly gives the angular position of the satellite in the orbit. But if the orbit is elliptical, then calculation of exact position is very difficult. At the time, mean anomaly is used as an intermediate step. So that is the need of using mean anomaly. Next, what is argument of perigee? A satellite orbit cuts the equatorial plane at 2 points, right? The first point is called as descending node, where the satellite passes from northern hemisphere to the southern hemisphere, right? Second point is called as ascending node. Like when we take first point, northern hemisphere, and second is southern hemisphere, that is called as descending node. And second point is called as ascending node, where the satellite passes from southern hemisphere to northern hemisphere. So in their movement, when it goes from northern to southern, we take descending node, and southern to northern we take ascending node, right? So argument of perigee, which is represented by omega, it is the angle between ascending node and perigee, right? If both perigee and ascending node are existing at same point, then argument of perigee will be 0 degrees. Argument of perigee is measured in orbital plane at Earth center in the direction of satellite motion. Next is inclination. At what angle something is inclined? If I take the horizontal plane like this, the inclination angle will be at what angle the orbital plane is inclined, right? So if this is my Earth, this is with this line I take the horizontal plane. If satellite is revolving like this in this orbit, then the angle, this angle will be inclination angle that it makes with the horizontal plane. This is represented as angle of inclination, the angle between orbital plane and Earth's equatorial plane. Earth's equatorial plane, right? So this is your angle of inclination. It is measured at the ascending node. We have ascending node, descending node, right? Now, if based on that, based on the angle of inclination, we can divide the orbits as equatorial orbit, polar orbit. There are orbits, like I have drawn Earth's surface. If some orbit lies within the equatorial plane, that is with angle of inclination 0, that will be called as equatorial orbit. This will be polar orbit, that makes 90 degree with the equatorial plane. Prograde orbit, angle of inclination lies between 0 and 90 degree, right? Retrograde, angle of inclination lies between 90 and 180 degree. If from here we are calculating, right? So like that. Right, escalation of ascending node. We know that ascending node is the point where satellite crosses the equatorial plane while growing from southern hemisphere to northern. Right escalation of ascending node is represented by this symbol which looks like omega, so O, right? So this is the angle between line of Aries and ascending node towards east direction in equatorial plane. Aries is also called as vernal and equinox. Satellite's ground track is the path on surface of Earth which lies exactly below the orbit. So these are few definitions that we need to know. Now if we talk about orbital equations, the forces that acts on satellite. A satellite, when it revolves around Earth, the forces in both the direction needs to be balanced, right? If this is Earth, this is my satellite revolving. If satellite needs to hold its position at this point, the forces acting outwards and inwards must be balanced. We know when a body revolves, there are centripetal and centrifugal forces acting on it. Centripetal force will act inwards, centrifugal force will act outwards. So when these two forces are balanced, the satellite or the moving body remains in its orbit. So mathematically, centripetal force can be represented by Gm by r square, where is the universal gravitational constant, right? And capital M is the mass of Earth, small m is the mass of satellite, where r is the distance from satellite to center of Earth, right? Value of capital G is given here. And if we talk about centrifugal force, the force which acts outwards, can be shown with kinetic energy, right? So F2 equals to mv square by r, the velocity with which it is moving, mass of the body, and r is again the distance between both the bodies, the central distance. So this is the centrifugal force. When these two forces are equal, when these two are equal, then the satellite remains in its orbit. So if I want to calculate orbital velocity, small v can be given by equating these two forces, which comes out as under root of Gm by r. Orbital velocity of a satellite is the velocity at which satellite revolves around Earth, right? When these two forces are balanced, we may calculate the velocity by which satellite is revolving, right? We are familiar with the terms. Capital G is the gravitational constant, its value is written here. Capital M is the mass of Earth, these are standard and fixed values. R is variable depending on the distance, and hence we can say that orbital velocity mainly depends on distance of satellite to the center of Earth, as your G and M are constant. That's all for today. Thank you.